So good morning, welcome everybody. Thank you all for coming out for the hackathon. My name's Ian Flint, and I work for Verizon Media, which is, in our case, it's the combination of Yahoo and Edgecast, the Edgecast CDN. So today we are going to be hacking. I got a little feedback. Turn that way. We're going to be hacking on Panoptes, and so I'd like to talk a little bit about Panoptes. Panoptes is our open source monitoring platform. It's built by the team, and we open sourced it about 2 years ago. And what it is, the problem we were trying to solve was we had a bunch of different pollers, a bunch of different metric systems that were hitting our routers. Some of our routers were being overpolled, 4 or 5 systems hitting them at the same time. And so what we needed to build was we needed to build a system that could both poll network devices, but also had a distribution bus and the ability to build different clients to do different things with those metrics. So for example, you might poll something once and send the metric to a capacity planning system, send the thing to an anomaly detection system, send it to a graphing system so you can actually see what's going on. So the idea was, rather than having separate polling for every single system that needed this data, that you'd have a single polling agent with a distribution bus. And in order to do that, we also needed to build some other features into it. Needed to have enrichment, so you get your data. Maybe you know that this particular interface is doing a certain amount of traffic. You want to say, what is that interface connected to? Which client is using it? And so we're able to enrich the data as it comes through and make it more meaningful to the downstream systems. And finally, when we open sourced it, no monitoring system is good without visualization, and so we stuck a visualization system on it. We did an integration with InfluxDB. So out of the box, you have a InfluxDB integration. So what makes it special? It's able to scale. In our case, it's really big. We're monitoring tens of thousands of network elements, and we're doing, I think, on the order of 30 to 40 actual metrics per interface across our entire network. And so there's a lot of data flowing through the system. Battle tested, we've been running it in production for a couple of years now, and not without its hiccups, but we've definitely, it's been through sort of the production ringer, and we've proven it. So, if you were to adopt it, you would have reasonable assurances that it would work in your environment. Plug-in architecture, this is huge. So this is the ability to arbitrarily extend the system to do whatever you want. So if you want to do GNMI, for example, and actually take streaming telemetry, build a plugin, bring in the streaming telemetry, and you can translate it to a universal format and put it on our data bus. If you want to do a special enrichment, you've got special information you want to tack onto your metrics, the facilities are there to be able to do that. If you want to integrate with your own visualization system or your own alerting system, there's a plug-in spot there where you can actually plug in and do that. So the plug-in architecture is very powerful. And finally, it's open source, so anybody can use it. So scale, I talked a little about this. On the order of 10 million time series are flowing through it right now in our production environment. We're monitoring hundreds of thousands of network interfaces, tens of thousands of network devices, and this is interesting, distributed across hundreds of sites. And so, we actually have a global footprint of this that's monitoring stuff across every single POP, every single data center that Verizon Media has. And how's it evolving? So actually, Panoptes has been a journey that NANOG has gotten to witness firsthand. We actually announced Panoptes in 2017 at one of the NANOGs. So 2018, we open sourced it, announced it here. We spun a Docker image in 2019 to make it more accessible to customers and easier to install and work with. And this year we've been working on open sourcing our plugins. So we originally released Panoptes without a whole lot of plugins, without a whole lot of integrations, but we've been working on open sourcing as many of these plugins so that you have good functionality out of the box and you're able to monitor real network devices. And so the team, me, I don't really do anything. We've got Varun. Varun, can you raise your hand, please? Varun in the back there. So he is the architect of Panoptes. It was all his idea. Nathan right here, back there. Nathan and Ian right here, and James are the active Panoptes team right now within Yahoo. So they're the ones actually doing the work, and they're the ones who will be walking around helping you out as you start to kick the tires on this infrastructure and figure out how it works. That is all I got. With that, I'm going to hand it off to Varun Varma to talk about the architecture.
Yes. Okay. Thanks, Ian. Hi, guys. My name is Varun. Like Ian mentioned, Ian had hired me into the team, I believe, late 2015, describing all the problems that he described. The problem wasn't that we didn't have monitoring. The problem is we had too much of it. We had, 7, 8 different systems all trying to do similar things, if not exactly the same thing. And the idea was to build something that unifies them, collects data once, but lets you do interesting things after you collect the data. There is one small thing. I now work for LinkedIn, but I never asked them permission for this event. So I ignored that. And LinkedIn does not use Panoptes, so. Yeah, so let's just call me a monitoring enthusiast. Okay, with that, let's get into the architecture. This is going to be a lot to take in, to be very honest. Panoptes, because it was designed to be a large-scale distributed system, honestly has a lot of moving pieces. So we've put an effort to make trying this out much simpler. James has done an awesome job of putting together a Docker container where basically not just try out the system, but actually develop within it. But it might be interesting to know the architecture, and when you guys get down to the actual hacking, some of the pieces will resonate. I guess the point I'm trying to make is don't try to take all of this in yet. But have this for reference when, during the course of the day. This stuff is also up on our site on getpanoptes.io, so if you need to refer back to this. But with that background, here is what we have. So we have a foundational layer, a set of services which we use across the entire platform. So we have Celery, which is a pretty popular Python-based job scheduling system. This is actually what gives Panoptes the horizontal scalability. You can just keep on putting in more hosts, and it just keeps on being able to do more work. We have Redis, which is a high throughput in-memory NoSQL store. Zookeeper, which we use for various things like distributed locking and master election. Again, being a distributed system, we've designed it not to have single points of failure, but that does require coordination. And Zookeeper is what gives us that coordination. And then we have Kafka, which we use as the message bus. Basically, going with the philosophy of generate the data once, but being able to consume it many times. So on top of these foundational components, we have the plugin framework. As Ian had mentioned, this is where the superpower comes in. This is not a fixed purpose system. A lot of people who've looked at Panoptes have come to the realization that, heck, this has nothing to do with network monitoring. You could do any monitoring with this. It's just that the first use case we put it to is towards network monitoring. But it's essentially the plugin framework that allows that. Now, we do have 3 types of plugins. I'm going to talk about this a bit here, go into a bit more detail, then Nathan is going to go into a whole lot more detail about plugins. But essentially, we have 3 types of plugins: discovery, polling, and enrichment plugins. And I'll talk about them in a bit more detail in the next few slides. But now, these are classes of plugins. What we have finally, the workhorse, is the actual device-specific plugins. Now, plugins, for the most part, is just Python code. Okay, it just basically has an input and output contract with Panoptes. But you could write basically any code you want, which does anything you want, which honestly is a potential security risk, but the reality, it gives you immense flexibility. We have SNMP and API plugins in our environment, but there's no reason you couldn't use SSH or RPC or any other mechanism that you need to actually write a plugin. Over to the right-hand side, I guess the slide's right-hand side is a set of services which are not core to Panoptis per se. These are services we actually use. So we have a time series database. In Verizon Media's implementation, there's a company-wide time series database that's available for us to write to. In the open source version, we've chosen to go with InfluxDB. We've packaged that as a time series database. But the point I'm trying to say is that while we need these services, services are not inherently part of Panoptis, and you're free to kind of plug in anything else you want there. There is a CMDB. You need to begin from somewhere. You need to figure out what devices to monitor. And in our case, the source of truth is again a company-wide CMDB. The open source version is literally a JSON file. You can plug in the name of the device you want to monitor into a plugin file, and that acts as the source of truth. And then internally, we have orchestration, because again, it's a large distributed system, so we have orchestration which sets all of this up and manages it. The open source version is again bundled up into a single Docker container. So really, on the three things on the right probably don't matter to you right now unless you want to start using Panoptis in production, which is when I think you should think about them more deeply. Let's talk about the core concepts: plugins, resources, metrics, enrichments, and how we do data encoding and distribution. Let me elaborate. I have slides for each one of these. Plugins, okay? So, like I said, they're just Python classes which have an interface. So there's a fixed input the plugins get, which, think about it, it's basically what is the device to monitor, some other metadata about the device, for example, the OS name and the OS version, what is the SME community string you should use to monitor the device, or the API password you should use to monitor the device. This is all input the plugin can expect, okay? The output that the plugin produces is again very well-defined set of classes which you have to stuff your data into, and I believe Nathan is going to go into a lot of details about that. And again, this is documented in detail on getpanoptis.io. And because they're Python classes, they can process data from any source, anything, SNMP, CLIs, APIs, anything we've not thought about yet. Okay, but they could consume data from another Kafka bus if, for example, you have some system which already is collecting data. As I mentioned, there's three types of plugins: discovery, enrichment, and metrics. I'm going to go into these details now. What is the difference between these plugins? Oh, sorry, I'm going to talk about resources and then come back to that. Okay. Another fundamental concept in Panoptis is resources. So resource is what should be monitored, okay? In a simple context, or in the network telemetry context, a resource most often is the device to monitor. But think about this, for example, let's say you want to talk to the peering DB API, okay? That is a resource that you would define, because you take actions against resources and you define the resource you want to monitor, okay? This is where resources are discovered through discovery plugins. Discovery plugins' job is to populate the set of resources Panoptis can act on. And this is, in our case, like I said, we use a configuration management database to pull this data down, but it could be anything. The open source version is a JSON file. You could integrate with a flat file, anything you like. Just to literally let Panoptis know that this is a set of things I want to get data from. There's two key elements to a resource. There's an ID, which has to be unique throughout the system. There is an endpoint, which is what the plugin will actually talk to. So think about it this way. Again, for an API, an endpoint would be the URL. For a device, the endpoint would be the device name, for example. Okay, but if there are other use cases that come up, those are the abstractions available. And then there's a lot of any amount of associated metadata that you want. Again, in our context, in Verizon Media's context, the metadata that we store is the make, model, the OS for each of the resources that we're trying to monitor. which allows us to do something interesting. So we have a specific DSL in Panoptes to actually select resources to act on. So again, Verizon Media has a very high change of rate network. So because there's so many devices and devices are being added and removed all the time, we cannot have a fixed set of resources defined. We can't have like, here's the 20,000 network devices that we will monitor. These keep on changing all the time. So discovery plugins, obviously can rediscover those devices to monitor. But here is another problem. So let's say I added a new Cisco device, right? Now, how do I tell the rest of the system that I want these actions to be taken on all Cisco devices? Okay, and that's where the resource DSL comes in. So you're not configuring monitoring against an IP or against a host name, but essentially a class of devices. So in our case, we've designed this that, hey, anything that meets this criteria, pick that up for monitoring. Okay. Like I said, this is going to be a lot to take in. A lot of this is going to make sense when you guys actually get down to the hacking, but context. The other core concept is metrics. So resources is what you act on, right? Metrics are what you actually collect from the devices. Okay. Metrics are a specific type of information that you collect from devices. Just a quick show of a hand, who here has worked with any kind of time series databases and, for example, know the difference counters and gauges? Okay, not a lot, so let me delve into this point a bit more. A metric specifically has to be a number that has to be measured, okay? If you want to collect data which is not a number, that Panoptes has abstractions for that, but please be clear that it cannot be a metric. So a very simple example is the bytes in, bytes out counter on an interface. That's a metric because it's a measurable number. The interface name is not a metric because that's not a number. It's a textual description, okay? Metrics by their nature typically are fast changing. So between two pole cycles, typically you will see the metric change. Now that's not necessarily true, but the key point to remember here is they have the potential to be fast changing. They're not necessarily fast changing. A good example is, for people who are familiar with network operations, is a network's admin status, okay, is a number. It's up or down. You can represent it as a number, up or down, 0, 1, right? Now, that doesn't keep on changing on every pole cycle. I mean, it can, if it's changing in every pole cycle, you obviously have an operations problem. You have a flapping interface. But the point is, it can potentially change because it's operational state. And that's something you should think about as a metric, okay? Again, you could collect it through any of these means because plugins let you collect data through any possible mechanism. The counterpart to metrics are enrichments. Enrichments are data that you want to collect, which is not a number. Enrichments are what are called tags or labels in some time series databases. What they are a way to add more context to a metric. So for example, you get the bytes in, bytes out from an interface. Which interface? How do you define that interface? So at the very least, you'd probably collect like an IF alias or an IF description of that interface to actually say, okay, it's this interface which has this bytes in, bytes out, okay? But why stop there? I mean, actually, to be honest, even that's not sufficient. The other metadata that you need is which device, right? Because ETH0, but ETH0 where? So that's another enrichment that you add. And then this can go ad infinitum. For example, there are enrichments that you can collect by talking to the device itself, because when you're getting counters from a device, you know the interface you're getting the counters for, you know the device name. So that's straightforward. But let's say you wanted to collect the geographical region that device is in. Is it in North America? Is it in South America? Is it in Asia? So that you could do actually richer reporting, right? That's an enrichment. That's an enrichment that you don't collect from the device because the devices don't know where they are. Some devices let you configure it, but as a general rule, it's not inherently a device property. It comes from somewhere else. So the other thing to remember at enrichments is, while they describe a metric, they don't necessarily need to come from the same source as the metric comes from. Another example is, how many of you are familiar with PeeringDB here? Okay. Not a lot, but one of the use cases pairing DB has is to let you map an ASN to a name, right? So when you're collecting pairing information from a device, you'll get ASN numbers. You'll get 1701, whatever, right? And that's meaningless to a lot of people. To a lot of network operators, it's not. Like, they know off the top of their head what the big ASNs are, but for most general users, it's going to be meaningless. There is an external API available that lets you map it to a company name. This ASN maps to this company. I'm embarrassed because I've forgotten Verizon Media's ASN, but that is again an enrichment. But that's again an enrichment that doesn't necessarily come from the device itself. The device doesn't know what ASN which company owns that ASN. Okay. Yeah. So, and I'm giving you this context because when you're building plugins, don't feel that enrichments have to come just from the device. In fact, some of the most valuable enrichments you can come up with are actually mashups from different sources. Okay. Now, enrichments typically, because they're not numbers, they're typically more expensive to process. They could be dictionaries or strings or basically any Python data structure. But obviously they have a higher cost overhead. So what we do within Panoptes is we actually, when you look up these enrichments, we cache them. It's configurable. You can decide how long an enrichment should be cached. Again, the thing to realize here is, therefore, enrichments pick things which will not change frequently. An IF name, an interface name can change, but usually in practice doesn't change that frequently. So that's something you should think about as an enrichment. There's cache invalidation mechanisms within Panoptes, but that's very detailed. But the point is, stuff that you're going to use to describe the metrics, you want to look up once and sort of cache for some time. We usually cache between 15 to 30 minutes. So it's not a very long cache. It's not a cache that goes on for days. But it's also not something that we collect on every cycle. And by Ian making this point that we collect like 30, 40 metrics, the amount of enrichments we collect per interface is actually double the number of metrics we collect. There's actually more metadata that we use to describe the interface than the metrics itself we collect. And if we were to do that on every poll cycle, the system would be that much slower. So what we typically do is, because we asynchronously collect enrichments, cache them, and then use them in every poll cycle, we basically can be more efficient and we can scale better with this. The other aspect is data encoding, distribution. Day one, Panoptes was designed as a distributed system. It was not a single standalone system which was retrofitted to be distributed, but it was designed as a distributed system. What that means is that these three phases, discovery, enrichment, and polling, are completely decoupled from each other. They work at different paces. This can be sometimes difficult to wrap your head around. Again, the Docker container, James has written helper tools which can actually help you understand what's going on and what stage the system is in right now. And there's documentation as well. But please be aware that things will not necessarily work exactly in a sequence because they're all decoupled from this. So for example, you start a polling plugin, but discovery has not completed by now. What will happen is the polling plugin is going to fail. It's going to say, yeah, I have nothing to monitor, right? Only when discovery finishes will the polling plugin succeed. So things like that, which are the nature of a distributed asynchronous system. We use Kafka to pass data. We use Redis for some small cases, but it's mostly Kafka that we use to actually pass data. We encode all data in Panoptes using JSON, which is supremely inefficient. It's extremely non-performant. It's a conscious choice we made in terms of, developer productivity. And actually even Python per se is actually a choice in terms of developer productivity rather than performance. So with all that context, this is kind of what the workflow looks for us. We collect data, plugins do this. We support some amount of post-processing within Panoptes. Right now, the only post-processing that we have is being able to convert a counter into a gauge, which is basically, you get the number of bytes from a interface. That's going to be an ever-increasing number because it's a counter. It's going up and up and up. But as a network operator, you're not interested in that. You're interested in the rate. How many bits per second does this translate to? So that's a transformation. And we do that in post-processing. Once we do this, we place the data on the message bus, okay? And then we have multiple downstream consumers. We have a time series database consumer, which again in the open source case is the graph is InfluxDB. And you can set up alerts on that also. Internally, we use OpenTSDB. And internally, we also send the data to a Hadoop grid for patch analytics. We also have another flow which we've not open sourced yet. We also send this data to a MySQL server and to build a to build purpose-specific APIs. I actually have a slide about that later. But basically, this is longer-term historical data. This is faster, instantaneous data. I think some stuff I've already covered. We wanted this to be horizontal scalable and no single points of failure, which kind of are, do make the system complicated, but those were what our requirements were. Like I said, Python is developer friendly, it's not performant, but that's a battle we actually had to fight with the technical council inside, saying that we understand that we're signing up for Python, we understand it's going to be slow, but we're doing it because we think it'll be easier for us to pull in more developers. On our scale, when we deployed everything, we broke everything. We had to do a lot of tuning of these components. If you guys, when you guys consider running Panopties in your environments, please be advised, the Docker container is great to get started, but that's not supposed to run at scale. You'll have to set up clusters for everything, and you'll have to tune these components. This is just a reality of how these things work. I'm actually going to skip over this slide. If you guys are really interested, I can come back to this because it's not only very useful in the context of the hackathon. I mean, this is how we kind of have a divide and conquer strategy of not transmitting data across all our data centers, but yet making it look like that the data is available instantaneously. Some of the operational experiences we had is one thing that was extremely painful. How many participants do we have who are from a network device vendor company? Arista, Juniper, you guys, I have choice words for you. Our single biggest time drain was getting and normalizing these metrics. Ian Holmes, who's sitting right up here, has done phenomenal work in terms of making sense out of these metrics. CPU from one device does not mean the CPU from another device. And that was, we chose a strategic decision to take that hit up front rather than just expose that data to a user who now has the cognitive load while looking at a dashboard to figure out, oh wait, this is this device with this release, therefore this is how I should interpret the CPU, versus this device from this release has a different interpretation. So we put a lot of effort in normalizing these metrics so that when a user looks at it, they can actually make sense of what's going on. Verizon Media, this is a fact, this is an SNMP shop. It's ubiquitous. Verizon Media is a multi-generational, multi-vendor network. There are some much more performant technologies out there. There's APIs, there's streaming telemetry. But SNMP, honestly, is still the lowest common denominator. It's something we can reasonably expect to work on our entire fleet. SNMP performance sucks. It's a 22-year-old protocol. It was designed for a different day and age. It was designed when network bandwidth was really expensive. They spent a lot of CPU time compacting it. And there's a lot of there's a lot of design decisions which made sense 22 years ago, which make SNMP not performant today. API performance is definitely far better. The other issue was when we were building this, we had some use cases of what we want to do with the data. We didn't have all the use cases, but we kind of knew that if we produce data, we will be tempted to use it in different ways. And that's proven to be true. I think we already have 3 or 4 different consumers. I think we've only open sourced one, but we have multiple other consumers which take the same data and do something interesting with it. One other key thing is, So a lot of our partner teams, infrastructure teams, planning teams, they want to get to the data that we've collected, and they say, "Hey guys, let us just why don't you just let us hook into your Kafka bus, and then you don't have to worry about it. You produce the metrics, and we can consume it, and everybody will be happy." We've taken a stand not to do that. The reason for that is when you do things like that, there's a particular on bus serialization format that we've chosen, or there's a particular Kafka client version that we've chosen. The moment you allow users to actually hook into your raw systems, changing means that you have to coordinate with everybody. So what we've done instead is, and it's been harder and it has a performance hit, is to actually store the data and make it available through an API. Because that way what happens is we have a very clean contract with our customers. And if we need to change anything, we can change it behind the scenes but as long as we keep the API the same. But it's just, a word of advice if you guys are considering consuming Panopti's data. Consider, to your partner teams not exposing the raw data as you produce them. We have some custom UIs as well. I think I have some screenshots. So this is one example of a purpose-specific API that we've built and a generic API that we get from the time series database. So it's actually a query for the same data. What we're doing is we're querying load balancers in both the cases. And at first shot, it's actually going to seem that the bulk and historical data query is actually simpler than the data for query for the real-time for the purpose-specific API. The problem is with the bulk or historical API, you have to learn a whole new query language. Think of it having to learn like something like SQL, not exactly SQL, but something like SQL. Not an insurmountable task, but what tends to happen is it creates a barrier to entry. Versus people who want to work with load balancers know what all of these mean. They're familiar with whatever there's on the left-hand side. So it's actually easier for them to get started. The other thing is the performance of the API on the left, which is purpose specific, is actually far better than the performance of the historical API. And the only reason for that, or one of the reasons for that, is because this is only built to provide the last point in time data. While the historical API will scan over all the time ranges that you specify, even if you're trying to just get to the last data point, there is a much more overhead it has to go through before it can return the data to you. So this is another experience we've had, is that we do need different APIs for different use cases. Okay. This is what our view looks like. This is the centralized telemetry system that we have within Verizon Media, which is based on OpenTSDB. The open source view looks different. Open source is Grafana. So how many of you played around, used Grafana? Okay. So the open source is just Grafana. It's well documented, and hopefully you shouldn't have any issues with that. So in our case, internally, because this is a big central cluster, we don't manage it. It makes operations for us much easier. But in addition, we also have custom UIs, which we've done. This is again a view of the load balancer. And you can see that the thing is, here we have simple charting, very useful. It helps you figure out trends and anomalies. But this is a completely different view. This is far more richer information about a load balancer than a simple set of charts would give you. So we've also built custom UIs. They've been built on the purpose-specific APIs that we've written. And this is all context. This is all what Panoptis is capable of. When you guys are thinking about hacks, when you think about using it internally, this is what all the platform will let you do. Okay, and with that, we will have, oh, hey. So what we do is actually this. We expose internally through MySQL, and the real-time API is built over MySQL, and the bulk API is built over TSDB. So in the open source example, it'll be the InfluxDB's API, which is a very well-defined API to query the data that you produce.
So there's no streaming API, there's no way to get a normalized view of what would be in a Kafka?
As of right now, you could query InfluxDB.
But Kafka is sort of a push of the data out. You'd have to query influxes pulling from it.
Right, right. Yes, you're right. There is nothing right now which streams out the data which is collected. So it does become a pull system. Yes.
Only we had some people hacking on the system.
Yeah, I know. Yeah, yeah, and that's not a bad hack actually, to be honest. Yeah, it's a pretty good. It's actually I think one of the suggestions we have as a hack idea.
How do you prevent multiple devices from showing up as discrete resources? If you have different kinds of topology discovery,
Okay.
do you do any kind of unification or to prevent?
So yes, a couple of things. That's where a resource ID comes in. What we simply do is we use the device name as a resource ID. That makes it unique. But that's a problem that Panoptis doesn't inherently solve. It's a problem that Discovery plugin has to solve. Because, again, there's some reasonable assumptions we could make about some topologies, but we can't assume all topologies. So the Discovery plugin would have to have that logic. By the way, another thing, generally, as we don't actually do topology walks to populate resources, there's a potential security risk there. So basically, there's an unauthorized device plugged into a network. If we discover that device as a neighbor of some other device, and now what we do is, we're like, yeah, this is our device. Let's hand it all the credentials we know. So there's a very big risk. So we've taken a conscious decision that we bubble up differences between what our CMDB says and what our topology says to our security team. And we're like, guys, we thought we were supposed to have X devices, we have X plus one device. Can you please tell us if this X device is supposed to be? And if it is, it goes back into our CMDB database. That's an operational call that we've taken. But if you're absolutely confident of your network, you could do discovery through topology. You could do topology walks to build your list of resources.
One last question. So for a device, some of my devices may support streaming telemetry, some of them may not. Some of them I may have some data I need to get from router API or CLI. Is there a place where you say, here's how I monitor specific metrics for a device? Or I'm a little fuzzy on the combination of metrics I want to grab from type of device, from devices, how you get the completeness of everything, which might be a combination of router API, CLI, and SSMP.
Okay. So for that problem, what we've done is we've actually published 2 data models. Oh shit, we've published 1. Yes.
Even though Avi is loud, it's still hard.
Oh, I'm sorry, guys.
Thank you very much, Avi.
The question that I was asking was, I have a set of devices which may be hundreds or thousands, but for a given device, I may have some things like optic temperatures which only get from CLI. I may have some things which are only router API, and then I may have some things which are SNMP, and then some things like QDepth that I can only get from streaming telemetry, and because of our wonderful beloved router vendors, I might still need SNMP. So how do I describe for all my devices, for all the metrics that I want, how to grab them?
So there are 2 parts to this problem. What we do is we define schemas by contract. So we define, I had said we make a lot of effort to normalize everything, and normalizing does sometimes mean choosing the lowest common denominator. So what we've done is we've published this is on getpanoptis.io for system metrics. What is it that we will collect across all the devices? What is optional, what is mandatory? Now, unfortunately, unfortunately, this is a design by contract. It's a schema which is well defined. It's actually like literally a schema that you define, but it's not enforced anywhere. So you could write a plugin which doesn't conform with that schema and things will still work. But what we would highly recommend you to do is look at the schema, write a plugin that conforms to the schema, because think about your end-to-end system. There'll be downstream systems which will make some assumptions about the data that are coming in. So as long as you adhere to that schema, the whole system gets the benefit. Okay, so that's one part. I just realized we've not published one other important schema. Maybe I'll do that during the hack day. But the other part to your question is, so this is what we expect a plugin to produce. The other question is, you're absolutely right. It's extremely common that It's not uncommon that we have to collect data from multiple sources. So this is where the genericity of the plugins come in. It's a Python script. So if you need to make out multiple calls, we actually do that. There is a specific plugin which makes SNMP calls and API calls and CLI calls because the data is not available in one place. But once it's done all of that, in the end, it produces output per the schema. Does that make sense?
So, yes,
Oh, yeah.
yeah, so you have to have, it's a per device type. You have
Yes.
a plugin per device that encodes all the unique logic for that.
Yes.
Per device come operating system version?
Yes.
Yeah, okay.
Dude,
That's the world.
there is a this is the funniest story I have. Okay, guys. There is a platform vendor who on a certain platform reports the temperature sensors at 1 million. I mean, it's not a scaling factor issue. Most of the temperature sensors are fine. There's one temperature sensor which reports a weird value. This is the funniest. I mean, I was laughing and crying. Ian made this change. He literally encoding the melting point of steel into the code and said, if a temperature comes more than this, yeah, let's cap it at the melting point of steel. The reality is devices are going to report random shit and we have to deal with it. And that's exactly what the heavy lifting the plugin has to do so that the users don't have to do it. Sure. Sure. So we want to start doing OpenConfig, but there's a few things to realize there. First and foremost, OpenConfig defines the syntax, not the semantics. A vendor can still misreport a CPU. It'll report it like a OpenConfig in the structure that OpenConfig wants, but what prevents a vendor, or the example I just gave you.
Percent versus total.
Yeah, exactly. The semantic interpretation and implementation is still left to vendors. There's a vendor who just decides to report the load average of a CPU as the CPU utilization. And nothing prevents them from passing an OpenConfig certification with that data. You still would have to massage the data. The other thing is OpenConfig is nascent. There are some really good things about it, that it's operator driven and things like that. But remember another thing, source SNMP is highly structured. Nothing prevents vendors from, and there's specific examples, I'm not going to call them out by name, but vendors don't entirely implement, remember OpenConfig lets you extend and override models. There is a vendor that extends and overrides the model and does not provide interface error data with OpenConfig. OpenConfig is a step in the right direction, it's not a panacea. That's, I guess, what I'm trying to say. Any other questions? Okay, awesome. Hey, Nathan, take it away.
Hello, welcome to the Hackathon. I'm Nathan, and I'm going to be talking about polling plugins and the life cycle of a polling plugin. So this is the display of the Panopti's architecture as presented earlier by my colleague Varun. We have external open source projects we depend upon on the bottom, Celery for task scheduling, Redis, our in-memory key value store, Zookeeper for locking, and then we have the message bus Kafka. We have Chef and time series database on the right, Framework, which provides the hooks to the external services and kind of stitches the bottom dependencies and the plugins together. And then we have device-specific APIs on the top. But for this talk, I'm really only going to be focusing on polling plugins and the interaction between the plugin framework. So what is a plugin? A plugin is a combination of two files. As you can see on the right, we have a Python class to load. You can put anything you want in this. You can import external Python libraries and use them, call functions on them inside of the code. You can make an SSH or SNMP connection to a device. You can import the requests library and make an API connection. So really, anything you can do in Python code, you can do within a Panoptes plugin. And then on the left, we have a config file. So the config file is what's loaded by the scheduler, and I'll discuss that in a minute. And you can see the module. So that tells the Panoptes framework where to look for the plugin. There's some documentation below, and then under the main section, there's the execution frequency. So we have this plugin. It does something. There's code in it. But how often do we want it to run? So within the plugin config file, you can make these specifications here. So right now, the execution frequency for this plugin is 60 seconds. So this plugin will be run by Panoptes every 60 seconds. The next item is the resource filter. So we have a plugin, but we need the plugin to run against a device or a set of devices. So we have essentially what's the equivalent of a SQLite database within Panoptes, and the plugin scheduler will take the resource filter and essentially query the database. So this one is saying resource endpoint is tutorial device. So it looks for a unique device ID and just returns that device, and the plugin will run against a specific device. But you can say device or resource vendor is equal to Juniper, and that'll return all the Junipers, and then you can specify and drill down on the operating system name. So this is just a DSL that allows you to specify what devices you want the plugin you've written to run against. And then finally, if you have any counters, bits in, bits out, unicast, packets out, anything, you can specify that here with the transforms, and that'll automatically provide rate transformation transformations for you. And here we specified errors in, errors out, so that'll convert that over the execution frequency, which is 60. So on top of the plugin file, there are two additional important processes that are part of running the plugins. As my colleague Varun said, we use Celery for task scheduling and have Redis for the backend for that. With Celery, there are two parts. We have the scheduler and the agent. What the scheduler does is it scans directories and it looks for the config files. It loads the config files module, and it uses the resource filter located to query the internal device list. Once it has the list of devices to run the plugins against, it creates a schedule entry for each resource ID and the plugin name. So essentially, when a plugin is scheduled, the task is added to the queue with the appropriate arguments. And in this case, it's just name of the plugin to run and the resource ID. And then we have the agent. We can spin up as many of these as we'd like across any number of hosts. These are processes that run plugins, and agents can load any plugins. They can run any plugin assigned to it. So it's very generic. So it will watch the Celery queue for incoming jobs. It constantly asks, do you have work for me? Do you have work for me? Do you have work for me? The second there is work, it's assigned, it receives a task, goes into a busy state, it'll load the plugin, execute it, and then handle the output accordingly. And a few slides down, I'll just be going into a step-by-step walk you through of exactly what the agent does. Just another data flow picture. This is the data flow of the polling plugins. We have a plugin run against some sort of device, SSH connection, SNMP, API query. Again, these plugins are Python code and they can do anything. They query the device, gets the results, some sort of post-processing occurs if you specify in the config file. It's then put on the message bus, and you can spin up any number of consumer groups to ingest the data and read it as you'd like. For instance, what we have built in the Docker container is an InfluxDB consumer that's set up with Grafana. So the second the metrics are ingested, you can automatically go to localhost 8080 if you follow the commands on getpanoptes.io, and metrics are immediately available. one of the consumers we're working to open source. We have a few Django applications that automatically ingest load balancer interface data and make that available. And then internally, we use a variant of OpenTSTB to ingest metrics. So the polling agent. When a polling agent runs, it creates something, what's called a polling plugin runner. And this is the task that constantly asks, do you have work for me? Do you have work for me? Do you have work for me? And when it does, it receives a task. And that's the combination of the plugin name and the resource ID. And remember earlier, a resource is a representation of a device or something that should be monitored. What happens next is the device lookup. So it takes this ID and it goes to our device store, which in this case we use Redis. So it takes the key, looks up the value, it'll return device data and some metadata about the device. And the next step is loading the plugin. Remember, we have the plugin name that was first sent to the polling plugin runner. So it looks through the current directory for all files that end in Panopti's plugin. And it loads all of this Python code. And then it applies the filter of the plugin name to it to determine which file to load. When it loads a plugin, it loads it into a class called a polling plugin info. This holds a reference to the plugin to execute, as well as all sorts of metadata associated with the plugin. So it has the last execution timestamp for the plugin name device pair. So when did this plugin execute last? It also has the last results timestamp. So when did this plugin execute last and actually return time series that aren't of length 0? So that's important for debugging. This plugin's running, but we're not getting results. Let's check the last results timestamp. Resource data. So we have some sort of metadata about the device. It also comes with a zookeeper lock. Before Panopti's framework runs a plugin against the device, it creates, or if it needs to be created, it will create it. If it's not, and if there already is one, it'll attempt to acquire a device-specific lock. One of the things we looked at initially was we don't want multiple plugins running against the same device at the same time. Overpolling was a big issue. So in order to fix that, in order to run a plugin, it has to acquire a lock, which is then released once the plugin is done executing. So it's a zookeeper lock. It has a reference to the key value store. This is where all the metadata is stored. So once the plugin is done running, it has to go back and update these values so it has the reference. And then there's the config info, like execution frequency, and basically the entire config file that I showed you initially. So next thing that happens, it checks to make sure that the plugin is able to be executed. So it checks the last execution time and makes sure that the execution frequency has passed. So 60 seconds, it makes sure that at least 60 seconds has passed since the plugin was last executed, and then it acquires the lock. And then what it does next is it calls the run method. If you look through the code a little bit, you'll see that all Panopti's plugins inherit from the Panopti's base plugin. This is an abstract-based class, so if you inherit from it, you have to implement the run method. This is, as you can see on the right, a function that returns Panopti's metrics group set, which is just containerized time series in our internal serialization format. Just records the start time, end time, calls the function get time series. You can implement that however you want. It can make an API call, do anything, and then log successfully pulled device, and then the time series are returned. So great. We have some results. In this case, it's interface unicast packets in for interface name EM1. We specified some rate transformations within the file, so it's going to perform those transformations, and the actual output is both a counter and a gauge. And then the output is piped to the messaging system, and it's consumed however the consumers are set up. So that's basically a plugin. It's very easy to hit the ground running. On the getpanoptis.io website, we have a starter SNMP plugin that'll automatically connect to the device you specify and make a few SNMP queries against interface OIDs. So that works right out of the box. It's very easy to extend that if you'd like to build some sort of SNMP polling plugin. We also, on the getpanopties.io website, we have a starter napalm plugin. So if you'd like to experiment using the napalm library against the Tsudo setup, the lab, you can copy and paste that right into your code base. It'll work right out of the box, and you can extend that as you see fit. So starter plugin there. And then we just have another plugin that makes API calls. So we have a few starter plugins if you'd like to work on plugins. And yeah, we have documentation at getpanopties.io. Next, my colleague Ian Holmes is going to be doing a live demo.
Okay, so starting from the top then. So they already mentioned the Panopties Docker container we have, and I have actually gone ahead and built that and have one running. But I did just want to highlight one thing, which is in my instance, I'm actually using, grab my mouse real quick. In my instance, I'm actually mounting in a directory that I have where I'm going to actually be updating the tutorial plugin, and then, hard to hear back there? Okay. If I lean in, is this okay, or is it just? Well, I need both hands free is the only thing. Here, testing, good? I can just hold it here. All right. There we go. Anyway, mounting in the files that I need into the appropriate place along the polling plugin path here. And then likewise for dropping in a localhost JSON file that we will be using for defining where our resources are coming from. Okay, so then I'm going to go ahead and just, yep. Awesome, so the first thing once you get in here, and this is just a separate step, is to actually run a populate redis shell script we have. And this is just a quick one-liner. Whoa! Maybe, testing? Not going to be able to cut that one. Okay. Take 4. All right. Let me just go off of this. Okay, so the populate redis is going to actually go ahead and just stick a secret that we have for for our local community site. And so you can configure multiple sites that you want a given Panopties instance to actually monitor. For simplicity's sake, you might want to define your resources all within a local site. And then if I actually just copy this down and do a get of this, in this case, this is a SNMP community string just for public. But I will drop that in here to show it off. And there we go. Okay. Awesome. So then, for any of the programming that you want to do today, you're going to want to define your resources first. So let me see here. I couldn't figure out how to make this sidebar larger, but just quick rundown of what I have. For configuration, I have this localhost.json file here. I don't know how to do or I've used it. I'm not. View presentation mode. Let's try. Yep. Let me just escape out of there. Fortunately, it's only a few. I can't get out. Back up there. There's only 3 files that are really important just for right this moment. One is this localhost.json. I'll go into in a sec here. And then the other one is our polling plugin code, so the .py file that we have. And then the Panopties-plugin configuration file. So then what we will want to do, and I've actually already dropped one in here, if you were to open this file up on your computer.
Sorry to interrupt.
Yes.
Does everybody have the Docker?
I
Yeah?
would.
Is anybody, raise your hand if you don't have the Docker. Okay, so go to getpanopties.io.
That's get, G-E-T.
Yeah.
Panoptes.io.
And then a lot of what Ian is going through is in the tutorial pages. So you can see a larger view, especially the mounts for the Docker start.
So the details about structuring a plugin is all there. Nathan wrote wonderful documentation for that, so I definitely recommend reading through that here to if you're doing plugins today to get started in a more, I guess, holistic understanding. I'm actually going to basically show the environment where what you have is the output of that tutorial, where you can find various files, see how everything's melding together. So what I've done here, and actually I'll just drop it back in. If you open up the localhost.json file, you should see this, which is a resource site. Make that a little bigger. For your localhost, resource ID set to the device name, like Varun was mentioning, and the endpoint, which is localhost. So I'm actually going to copy that in order to create a resource for one of the virtual devices we have today in our emulated network from Tesudo. And so I'm going to keep the other details the same here, but change the resource ID to, or the resource endpoint first to VMX. This is a virtual Juniper MX device. And the URL format that they have is vmx.the community name, which is nanog78, the organization name, which is Panoptes, and then .cloud.tesudo.com. And we actually have, if I scroll over here, we'll leave this up at the end here, but we actually have the devices that we've defined all set up here, just so that you know what you have access to. A couple of Cisco's, an Arista, a Juniper device, and if anybody needs Cumulus, come help us, because we don't know how to set up SNMP on it. We don't use those internally. Say? You did? Okay, wonderful. Feel free to hack on Cumulus. I may do that today. All right. So once we have this set in here, I'm going to go ahead and just copy that over to be the resource ID as well. So we define off the off the resource endpoint. And then if we drop back over into our Docker, we should see this already coming up. So let me real quick. Just going to do keys one more time here, and excellent. So we have our resource manager key value store here has already discovered the resource that we just defined. And if we do a get for this one, we can see there's a pipe delimited description of what that looks like. And so we can see that, again, actually here I guess we just have the timestamp that it was created and the resource TTL, so that's time to live. And so this is what we use to configure Redis in order to know how long to persist the resources that we discover. Okay. So then, okay, all right. So I'm going to hop on over to the tutorial plugin. And so again, Nathan wrote a really wonderful tutorial I recommend stepping through, which goes into the details of what you can find in each polling plugin. And it's nice as he's actually stripped away some of the abstractions so you can see exactly what you're working with. We're going to define a Panoptes metrics group set. And then in the context of run, we're going to grab, let me scroll up here, figure out where we have it. Grab an SNMP connection and then make a few queries to populate. Where am I looking for this? I think that's the case. There we go. Thank you very much. All right. So let me just do for SNMP. There we go. So for each of these, in run, we have a few commands for interface name, interface alias, speed, and then packets in, packets out. And then we're actually going to take for each of these, he's decomposed out methods that actually query the object ID that they're handed, steps over for each of the indices that are in those relative tables, stores it internally in the interface table, and then down here, when he actually does the populate the Panoptes metrics group set, is actually going to drop those in. So here we have where he's adding each of these given metrics as it's queried from the internal table. Okay, so then if I hop over now to, well, actually first let me show you a log here. If we just tail, so from home Panoptes, there's a logs directory. And let me just ls that as well so you know what you have access to. So you have the scheduler and the agent that Nathan was talking about for each of discovery, enrichment, and polling plugins. So in this case, we're abstracting away the enrichment plugin, so I'm just going to tail the polling plugin scheduler log. So that's going to be polling plugin scheduler. And we should see here, let me actually grab here. Okay, as intended. Let's see what we got going on here. That wouldn't actually be named there. So anyway, you can see the scheduler for the polling plugins now has 4 tasks, and so that would be running the plugins that we've defined against each of the resources. So we've defined 3 resources at this point, 2 of which or 1 of which is being run twice. So that's why we have a total of 4. And let me actually just hop over then to our Grafana dashboard. So localhost port 8080. And then I'll actually go to create a new dashboard and add a query here. Select the data source from Panoptes, and then I'll go to our interface data, and then set the resource endpoint, and we can see that it may be very small in the back, but there's localhost and there's the VMX that I was just mentioning. So if I click on the VMX, let's just grab, say, the packets in. I'm going to change the selector from mean, since we're looking at a specific device, to last. And we can see it's been coming in just for an hour or so, but let me just grab last 15 minutes. And so that this actually shows up better, I'm going to fill in from previous. We can see that it is actually getting these metrics already coming in. So just plugged in from that. And so what we also have then is, I'm just going to dart back over here, the excuse me. The tutorial plugin that we have right here, so I go back to the right one, is reading from it's actually querying the interface name, interface speed, alias, as well as the packets in and out on every polling execution. And so, unfortunately, I had to copy this over from another computer this morning, so things are a little bit misaligned right now, but I did want to show that it is actually possible to collect the seldom changing data, the enrichments for the name, the alias, and what was the other one that I just mentioned? Name, alias, and configured speed to be coming from an enrichment. And we actually already have a plugin enrichment interface that is stored, or that is up and running. So if I go back over to Redis real quick, I'm going to do echo, I'm going to grab keys, just see what I have for all enrichment real quick, and then here we have, so this is line 6 here, the plugins key value store. We're grabbing an enrichment for our virtual MX device and for the enrichment namespace interface. Like Varun mentioned, the enrichment's really powerful. I recommend digging into enrichment.py, looking at the enrichment schema, and seeing if it's of use to you to go ahead and configure that as well. I think many of you will probably choose to work entirely within the polling plugin framework today, at least to hit the ground running. But this is worth looking at. So let me do a get of that value. So copy this back over. Grab it from the Rita CLI, and then this is actually JSON, so I'm going to pretty print the JSON. And so for, oh, and I just remembered, I grabbed this from a virtual MX device, so there are a lot of entries in here, but you can see for a given port number, because it's coming from a virtual device, a lot of these are actually not set. But you have media type, defined, just various enrichments that are already collected by our interface enrichment polling plugin. And so we have a lot of descriptive data to show. And let me see if I can just get to the top here, just to show what the, and I overscrolled. Just wanted to show what the beginning hit. Yeah, and then we have metadata about that enrichment. So again, in this case, we're persisting the enrichment for 900 seconds or 15 minutes. And whereas Varun mentioned we typically would run enrichments every 30 minutes. For development, because it's just on a Docker container here, only a couple plugins, I have it running every 60 seconds so that you can iterate on it. Let me see here. So as I go through,
The TTL data from the enrichment expires. Then there's no enrichment.
so if the TTL, if the data expires, then it would disappear. So that's why you're relying on the enrichment plugin actually running, in this case, every minute, so that it will overwrite the data that was stored in Redis. So Redis is just, for those that may not be familiar, just a temporary key value store. And so you can define what you want the time to live to be of each element. For some of those, we have it configured to like a week, and in other cases, only for a few minutes, like here. So then, I can't hear you, Varun.
I believe the question was around the TTL. So the TTL is typically defined as multiples of the execution frequency. So even if one execution fails, we'd still be able to work with the cached information we have. In this case, it's almost 15x. But typically, it's not uncommon for us to define it 8 to 10 times of what the execution frequency is.
Right, but in this example, after 15 minutes, if you couldn't get the enrichments, you'd lose interface name.
Right, but the thing is, the enrichments will be updated every 60 seconds. So only if they're not updated for 15 minutes continuously, then yes, you would lose polling data. Because at that point, you're not sure if, how fresh your data is.
I just assume everything fails.
All right then. So then let me do one more quick check over on Grafana. And I believe that in this case, yes here. So here, let me just head back over to PyCharm. Just the last thing that I wanted to drive home, and I unfortunately have been working with this, and I think I have something just misconfigured on my laptop specifically. But if you wanted to actually, so in this case, again, these first three here, the interface name, configured speed, and alias would be what we would think of as enrichments that you could grab. And if you wanted to actually do that, or get them from an enrichment plugin, the way that that would look in code is that you would actually define, let me see here. Basically here we have Panopti's SNMP base plugin, and there's a subclass of that which is base with enrichment plugin. And then what you would do at that point is actually just add self.enrichment under your init to your properties, and then down here you would, to your attributes, and then down here you would actually define your enrichment. That would be defined from the context coming in. And so then what you can do, and I'm just going to show you what the line of code looks like, and then point you towards the other open source plugins to look for examples here, since unfortunately I can't do this portion live, is you would actually grab self.enrichment, just one sec, and then, let me see here, just scroll up here. Exact line of code. Yeah, .enrichment.get enrichment value, and then you're actually, what this is going to do is we're going to define the resource we're grabbing it for. So in this case, this resolves to self resolves to the resource ID that this plugin is being executed against. The namespace we're wanting to grab, so that would be the interface, and then this up real quick. And then for whatever specific index you might want to actually grab. So in this case, we would define the we would have populated a interface table like Nathan had already done previously in his example that I'm copying down, this interface table. And then we would loop over that, and for each of the indices that we have, we would actually then, so getting the enrichment into, we call this enrichment table. And then from the enrichment table, we would actually do, let's see here, enrichment table.get on the specific enrichment name like this. And then you would probably want to drop that into another, into the interface table or into some other internal dictionary that you would use to create your Panoptes metrics groups, and then use those to put into the Panoptes metrics group set. And like I said, so this is messy, but there are the other plugins that are open source that, that are a lot cleaner that you can step through. For those who are just starting off with it, I would begin with the polling plugins and then look at how they're using the enrichment plugins and see if that's something that makes design sense for you to pick up. I saw a hand go up over here.
In this case, you're actually editing the polling plugin itself to add the enrichments?
In this case, yes. So then you would also, I don't have it copied in here, but you would have a separate enrichment plugin that encapsulates your logic about actually going out, whether it's via SNMP, API, et cetera, to get that information. So I'm saying, pretending you've written that plugin, okay, this is how you would actually link it in. And I think that probably for most people here it would be more instructive just to open up one of the complete bona fide plugins and just look at where that's hooked in. The main takeaway I just want you to take from this is that where you see the Panoptes SNMP base plugin at the end of the tutorial that Nathan wrote, if you wanted to hook in an enrichment, then you can just call that base with enrichment plugin. And then if you're in PyCharm like here, you can actually just command click in order to go find the declaration in your code base.
But in terms of the process for, like for example, when we wrote the polling plugin, we changed the conf file and then we went into the Python file within that path and added that. Would we need to do the same things for enrichment as well? Change the config file?
Changing the config file, so actually, yes, and I'm glad you mentioned that, because here what we would do is, again, if we have this being populated, we'd want to add the enrichment section, and then there's going to be a preload key, and we're going to, that would be in this case self and the name of your namespace, in this case interface. Thank you for reminding me of that, because you could go drop this in, but you do actually need this configuration for it to run. Awesome.
Hi everyone, I'm Kaushik. I'm from George Mason University. I'm a master's student. This is my team, Hisail, Ruchita, Anamika, and Saiti. Thank you. We literally had no experience with network automation. Thank you. I thank everyone who helped us achieve what we have done today. We have gone through the website, and there was a tutorial. So we tried to create two plugins. One was the basic polling plugin, and the other was the Napalm plugin. And then we got an output. Yeah, we got an output like this on our local host, and then we still had time, so Nathan helped us add a few metrics to our Napalm, and then we added few metrics. One of them, they were last flabbed and speed, and then we added the metrics. We changed, we updated everything, and then we got the logs, and then we tried to pipe the logs into a JSON file, and then it was looking like this. And then this is how it looks, how the output looks on the local host when we add speed and last flabbed. This is all we could achieve. Yeah, this is all good we could achieve today. And thank you, Nathan. He helped us a lot. Thank you very much. And this is it. And thanks, NANOG, and all the sponsors for giving us this opportunity. This was more like a learning experience for us than like a hackathon. Like a hacking competition. Thank you. Thank you, everyone.
So, hello everyone. So we are Team Buffs, and we are master students in network engineering from University of Colorado Boulder. So today morning we got to know about Panoptis actually, and we know that right now it's a great tool for monitoring across all the platforms. So when Varun mentioned that we can add our custom own plugins via Python, so we thought we can add more functionality to Panoptis by adding configuration functionalities to that. So Panoptis is a tool which monitors everything. So let's add a configuration functionality once we get the alerts. So how we did it? So our hack was we added the custom plugins using Python, and once we got the alerts to the users via Slack, when we have a function which will kick into the picture, and it will configure and it will try to mitigate the problem we are trying to solve. So, and yeah, for the multi-vendor capabilities, we tested it on Junos as well as Cisco. And how we did it? So let's go to the workflow. So for monitoring, we have used netconf and SNMP. So due to time constraint, what we did, we had only one metric, that was our CPU utilization. So while we are getting the real-time CPU utilization values, we fed it into InfluxDB and visualized that using Grafana. So to say we had our CPU utilization like around 20% at particular point of time. So make it more than our threshold, we reduce the fragmentation on the interface. That's why the CPU utilization crossed our limit. So when our CPU utilization crossed the limit, then the Python program will alert to the network admin, and at the same time it will kick in a healing script. So how we did that? I'll go into the deep. So for the key implementations, for net configuration purpose, the healing script I'm talking about, that was used by netconf. And why we use netconf? As netconf is a generic template, it's a vendor neutral, that's why. So as a part of Panoptis, we have used InfluxDB, Grafana, and just for the alert mechanisms, we have used Slack. So our custom plugin was named as hack.py. As you can see on the left-hand side, that's on the CLI, that's our CPU utilization we were getting, and that were fed into our InfluxDB. So that's our visualization using Grafana. Just to explain, you can see there is one dot in the red area. So that's where our CPU utilization crossed the threshold value and the event alert was generated. So event alert was a thing where we were making sure that how many times the self-healing script was run into. So while we captured the graph, it was once the CPU utilization crossed 35, and we got that alert. For the alerting mechanism, we use Slack, and that is a Slack snippet where it shows that there was a CPU utilization error which had 36% over there. So to mitigate that, I just mentioned that we have used netconf, and that's XML format, the RPC call, we were pushing the MTU size of 2500 on the Nexus device. And it got, after configuring that, we just checked on the Nexus device. That was how it does say that the MTU was changed to 2500. So after our custom plugin, we had word with Varun, and he mentioned it, how we can integrate our custom plugin into Panoptis, and that's how we tried to plug in our custom plugin into Panoptis. Due to just short time, we haven't tested it very well, the plugin. Yep. And the future scope, what we can look for is we can integrate more sophisticated network monitoring as we have netconf. It might be differ according to the platforms. And why right now, due to time constraint, we have just used CPU utilization or metric, and we can add more metrics into that, as well as create the potential and the corrective actions according to the metrics. So these are our key takeaways. We learned a lot about Panoptis, how we can include the sub-processes, Grafana. The InfluxDB was new to me, and then netconf. So, and above that, we learned how we can leverage the power of automation and network programmability. So the teamwork, time management, and yeah, never give up. Anything we do that. So these are my team members. So they are sitting over there. And if you have any questions on how we did that, what are the codes we have run, you can anytime you can email us. And thank you so much.
Hi everyone, I'm Srinidhi, and those are my teammates Simran and Vinayak. We're a team from Juniper Networks. We also had another member who had to leave early. So what we did was, in addition to the basic plugin, we added a napalm plugin. And the focus of it was traffic visualization of a typical day for a network operator. So this was the topology that we were working with. Chris reserved a different topology for us. So initially, we had an eBGP fabric running eBGP, and then when we were pinging traffic between host 1 and host 2, it used to take the MX2. So even in the trace route, you can see that the traffic is going through MX2. So the scenario for a network operator is upgrading the devices. So if you want to upgrade the MX2, you steer the traffic away through MX3. So we wrote a custom application called drain.py, which would advertise suboptimal BGP metrics through MX2 and steer the traffic away. And then you see that it's taking it through the MX3 as the next stop. This looks okay, but the real goal was to actually visualize it and give more context to how this all looks like. So this is a detailed view on what we had on MX2. We were pulling the information from the napalm, and we resource MX2 and the interface statistics. And this is on MX3. We were visualizing the last seen packet value. And this is a more important slide because it brings it all together. We initially see that the traffic was all on VMX2, and on VMX3, the interface statistics is less. So when we run the custom drain application, you see that it becomes stagnant on VMX2. So the interface statistic, the last seen packet is the same. You don't see any additional packets, whereas it starts to grow on MX3. And it becomes constant there, and that's when you see it go down. That is a simulated upgrade of VMX2. And all through this process, we see that there are no packet drops. Now, granted that this was a ping traffic that we were running, if there were more traffic-intensive applications, we may have seen some packet drops potentially, but it's a good way to visualize it all together. And when we undrain it, once we're done with the upgrade, we see that the traffic is, we run a custom undrain application, and the traffic goes back to VMX2 as we see there. And in conclusion, we learned 2 new tools. We'd never worked with Panoptis before and Grafana either. So it was a good way to bring it all together. And I really liked how programmer-friendly the tool was with Python and JSON. It was a nice way, even though it was a short amount of time, we were able to work well because of how efficient it is coding-wise. And we had challenges with the polling scheduler. It was not, even though we had it in the Docker image build, the packages were not installed, like the napalm package that had to be there. So we had to troubleshoot a little bit of that. So we learned debugging. In doing so, we learned a lot of debugging. And the future work, we got a start on this, is to have a custom Kafka consumer, which pulls the data, and maybe data like traffic discards or traffic errors. You could report it to via email or tools like ServiceNow. We couldn't complete that, but that's probably a future work that we have. So it's a nice programmer-friendly tool and a multi-vendor tool. Coming from a vendor perspective, I think that's really cool as well. Thank you.
So we don't have a lot of great progress, so we are not going to get the Nobel Prize tonight. But I want to mention that I thank Nathan and then James for helping out. We were figuring out different things, and then this is what we get. We get the throughput of the network, and then the red means that this alert. And we also figure out the tool to find the OID value from online URL. We are trying to get more detail, but we kind of stuck on that. But since we have some time, we are going to bring back the history. Coming from Asia country, we have a lot of history. But so my colleague is going to share with you some of the history of the SNMP and other stuff. Hold on.
Yeah, so me and Henry is quite old, so we work in OSPF, and for me in FreeCom and BGP in the 90s. So this brings back a lot of bad memory. But I think one of the biggest challenge today in today BGP, because when it started, the whole thing was not ever designed for video input the whole thing. Today shaping this video thing is never ending chasing stuff. So wherever you have ping traffic have no meaning in reality of the whole thing. You don't know the source and client things and the codec, how they shape the part. So if the BGP code don't stay codec independent, which majority traffic in the internet today is video, it's just never chasing down the wall that is not manageable. Because original in 1996 and 2000, that was never the idea to do this video stuff. That's the reason why you need integration between codec and bandwidth and stuff like that to do so. So whatever you do, just remind me the application and the key. Sorry, Juniper. Ping does not work.
Okay, thank you very much again for all the help and learning about this wonderful tool.
So we have a team of folks made up from students and faculty at Purdue University, as well as an employee of Mythic Beasts. And so we would like to share with you what we have accomplished here today. Do I what? Like that? Okay. Louder. Okay, so we chose to add we kind of took a different path than other folks so far in that we added some new functionality to this Panoptis setup in that it normally communicates with InfluxDB and then displays through Grafana, and we replaced InfluxDB with Prometheus. And the reason being is that the InfluxDB is a great time series database. However, it has a couple of characteristics that we would like to offer an alternative for. And one of those is that it does not allow for high availability and horizontal clustering. So unless you want to pay. So it has that option, but it's closed source and for pay, and it's a chunk of change if you're looking to implement open source software solutions. And so Prometheus does have that sort of thing, and the licensing fee is free as in speech as well as free as in beer. I'm glad to be able to use that particular phrase outside of the university setting because you can't usually do that.
All right, so a little bit of extra background information, especially for people that may not have a full comprehension on both of these. InfluxDB versus Prometheus. Influx is a push-based system. which means if we want to make these changes for how frequently we're getting this information, we have to redeploy a lot of different elements, whereas on a poll-based system, we make that change in one location. It can save us time, it can save us computation. Additionally, if you're looking at both of the next two slides, they kind of correlate with each other. Influx, the way they store their values generally has a bigger impact on data storage. You're going to ultimately store 10 times, 20 times, depending on the metrics, you're going to store a lot more data for the same data set. And additionally, that can come at a higher CPU load. So this is something that we thought Prometheus could help solve. And then just a couple other things to add. Influx uses SQL variant, whereas Prometheus uses a simplified query model. That's more of a preference thing, doesn't really matter. What we will give Influx, though, is that it does have role-based access controls, whereas Prometheus does not actually have basic auth or RBAC at all. That being said, there are solutions out there to fix that. Placing it behind a reverse proxy can really help get it in that security stance. Oh, it's you.
So we had in order to implement Prometheus into the project, we had to change the layout of how it goes into the database. So originally it was pushing it from the Kafka consumer into InfluxDB directly. We had to move it so that it went into Redis. There's an intermediate database, and then pulled out of Redis into Prometheus asynchronously. So it would push into Redis and then pull out of that for Prometheus.
Okay, so to finish this off, a quick demonstration. So the InfluxDB variant looks something like this. And if we take the variant that we created, it looks something like that. So you effectively get the same set of data being represented using slightly differently structured queries, but you can get the same result using a database that is inherently very different and uses a different licensing model. So, yeah.
Okay, hello everybody. My name is Eddie Metzger, and I'm here with Team Rocket. And we had a problem that we identified. So we're going to run through kind of a couple of things here, and then demonstrate the solution script at the end. So we identified that there's an issue with troubleshooting. So mainly it's just expensive. You have these different ticket levels that are assigned, and it moves through this layer that takes too much time and too much money. So there are multiple types of packets, and all of them cost different things, but on average, they're costing you about $100 each ticket, which can add up throughout the months and then eventually the year into hundreds of thousands of dollars each year in just ticketing and solving these problems. And so, we recognized that there's a need for really kind of automating this process of troubleshooting and testing. And so with automated regression testing, you're ensuring that the features work as intended and don't negatively affect the environment that you're producing in. And so kind of assuming that you have a new device that you're running a new configuration on, this is where it becomes really helpful. And so why don't vendors always conduct this regression testing on new devices? It takes a lot of time. And so the plugin that we kind of developed or worked on and started to create really creates an automated troubleshooting environment to help you move through these levels of ticketing. And so it automates the process using automated regression cycles. So a couple of use cases would be testing new software for code and then testing custom solutions, POC for customers. And so finally, the structure of this is you configure a device with specifications and the devices that might have new ports. And then you run this automated regression testing on that new port using the plugin and address the problems immediately rather than in a future ticket.
Hello, my name is Hassan, and I'll just give a couple of minutes for the use case. So the use case is this about we open, customers have issues, they open up a ticket, and they have sometimes more than one departments involved, and you try to troubleshoot. The tickets is assigned to tier 1, tier 2, tier 3. But in this scenario, if we automate the matching condition for the Boolean ones and zeros, like if the route is coming from this router or not, or if there is a ping is going on from this router or not, then that would save and assign that portal to the specific customers. That would help for them to, in fact, diagnose where the problem could be in the first hand, so that they don't have to wait and see or call the NOC and save the resources and their times for the troubleshooting part. But right now, what we worked on, and another aspect of this is Cisco, Juniper, all the vendors, they're releasing new softwares every other day. And as being an operator, you want to make sure that software supports all the features and functions which you're providing solution to your corporate customers. So to test that automation and make it an automated solution, we need to configure and test those features on the new software codes. And that's what we tried in this first plugin. We were working on building one configuration template to push the configs on the devices and then test them that, okay, this feature is working. For example, for this is an OSPF neighborship. We're pushing the configs to configure OSPF on the 2 MX, which we got set up. And this is just the snapshots of the NAPOM plugin and the previous plugin for the just the output, so that we can see we already established the baseline for this. This one is the NAPOM output as well. And that's pretty much it. If everybody has any question, they can come up or we can explain. And the more application, just to quickly mention, David also mentioned we can use Ansible. If we integrate Ansible with the Panoply, it's going to help us a lot in the long run, where we can automate the jobs and do the monitoring at the same time of the results. Thank you.
Okay. Hi. So we seem to have two different classes of presentations here. We have the people who know what they're doing and the people who spent until like 2:30 or 3 o'clock trying to get their crap working. Do I really need the microphone? I'm really good at yelling. Oh. Darn it! Okay. As I said, we're noobs. There we go. So me, TJ, DJ, and Jay on. So, except me, I'm not a J. So this is what we managed to get working in Grafana. It's super fancy. I know I worked really hard on this. We worked really hard on this. There were very, very long paths, some including this in case anybody wants to reproduce any of this work. We're going to refer to them by the file names. Reproduction steps are from this getpanoptes.io document. And in that, I added the OID definitions in the Python script. I commented with what I added. How do we find those? I used the provided documentation or the Junos MIB Explorer and verify them on the router itself, since y'all kindly gave us read-only access. Reproduction steps, there were a couple of other places that we had to edit the polling plugin.py script. This is the second, third, and then we had to make a .panoptes plugin for it, which references those things. The wins were that it works. It was simple to get the same Docker set up on an EC2 instance with just additional port forwarding for Grafana. The struggles, there were too many shells, Python, Docker, and Bash, and in which shell everything was supposed to live. Changes outside the Docker container being for absolute naught and wasting a little bit of our time trying. Changes not immediately propagating, having to wait for some of it. Windows compatibility was a problem. Plugins crashing with no notification because lines that begin with 8 spaces that look like tabs are not actually tabs. and general complaining about the Mac keyboard. So you can either interpret this as how the noobs saw our day today, or you can say that Panoptes is on fire.
All right, so I think we're Team Neo4j, also Panoptes Graph. I don't like naming teams. Those of you who were at the last hackathon would remember Team Pod 1. But we did some interesting graph database stuff with Panoptes. So just a quick summary of what we did. We wrote a generic napalm polling plugin that all of our different vendor plugins inherited from. This polling plugin added LLDP data to our interface counters, as well as speed so that we could calculate link utilization. We then added a Kafka consumer that listened to the Kafka topic that Panoptes publishes to, and forwarded that data into Neo4j using Neo model, which is a ORM for Neo4j. Neo4j is a graph database. And then using that Neo4j browser, we plotted some pretty graphs. So this is what we wanted. This has the full, we hit some struggles, and while we hit those struggles, I inserted a bunch of dummy data into the database so that we could at least show you a pretty graph if everything went to hell. So this is the pretty graph we wanted. This is the pretty graph we got. So we actually got really, really close. We're only missing one set of links in there. So the problem we hit here was that Cumulus does not have a napalm driver, and we didn't have time to write a napalm driver for Cumulus. And the Nexus napalm driver doesn't have a get interface counters method implemented, which is really surprising because Nexus is a pretty popular platform, but so like I said, we got really, really close. One of the things you can't see on this, because we didn't get a chance to do any fancier interfaces, is that we actually store speed, port names, et cetera, on that link relationship. And so you can actually query that data out of the graph database. And if we'd had more time, we would have had some pretty colors on these links to demonstrate utilization. So challenges we hit, like I mentioned, napalm support. Cumulus totally unsupported. Nexus had broken interface counters. And then iOS XR, the counters were just, or sorry, Nexus didn't even have the interface counter method, and iOS XR was not correctly reporting counters. So we didn't get the, the pretty numbers we wanted there. And then the big issue we hit is we found out the hard way that Panoptes doesn't support relative imports in your plugin file. And so we spent God knows how long debugging that, hence me frantically filling the graph database with dummy data. But we found it eventually, and we got Panoptes working. So next steps, obviously, napalm support or replacing napalm with some other device interaction layer, adding that pretty coloring, building a more kind of advanced interface to that graph database. Like I said, we just use Neo4j browser for this, but there are a lot of really cool JavaScript libraries out there that can connect directly to Neo4j and do more advanced display. And then finally, doing something more interesting than just topology maps with this data. I mean, with this data in a graph database, there's kind of a ton of different applications out there. So this is definitely a starting point for a lot of other interesting work. So thank you.
Okay, we have a number of votes in, and we're going to call it, with the top two teams being the Neo4j graph team and the Purdue teams. And of course, a huge thank you to everybody. So we're going to do a couple more things before breaking here. So the first order of business is having at least one person from both of those teams come and see me afterwards, so we can wrangle presentations for the plenary session on Tuesday.
All right, thank you everybody for coming out, and congratulations to all of our winners. And I'd like to put in a plug right now to say, if you did your hacks and you're proud of them, contribute them back. Do a pull request against the hackathon base, and yeah, let's get some community involvement and get people contributing to Panoptes. So yeah, thanks again, and the reception is out under the giant mysterious copper ball in the lobby. So we'll see you all out there.